Welcome back, and in part 4 we'll be looking at an example of the Thevenin equivalent network, another one. This time we're going to be looking at this circuit. It's a linear circuit. All it contains are independent current sources, an independent voltage source, and 3 resistors. And the first thing we're asked to work out is what is the resistance in the Thevenin equivalent network for this two-terminal linear network. And since we have independent sources, we can apply the trick. We can set all the sources to 0 and then just look at what the equivalent resistance would be between the two terminals A and B. So let's try that. If we set the current sources to 0, then we're replacing them with an open circuit, just nothing. If we set the voltage sources to 0, then we're replacing them with a wire. So we would end up with a circuit that looks like this. This is a 2K resistor, this is a 2K resistor, this is a 1K resistor. This is the wire that's replaced our voltage source. This is the gap that used to have the current sources in them. Well, if we look at the total resistance between A and B, no current would flow through the 1K resistor here in this circuit because it's got nowhere to go, so we can just ignore it. We've now got two 2K resistors in parallel. And if you can remember the special result when you have 2 equal resistors in parallel, then the equivalent resistance is just half of each of the resistance values. So 2 2K resistors in parallel behave like a single 1K resistor. If you can't remember that special case, then you could just put the values into the formula. You'll get out the same result slightly later. So our Thevenin equivalent resistance is just 1K, 2 2K resistors in parallel. Next, the Thevenin voltage. Well, the Thevenin voltage is a little harder to work out, but the Thevenin voltage is the open circuit voltage. So it's the voltage that would appear between A and B when there was nothing connected to the network. How do we work that out? Well, the easiest way is to use the principle of superposition, which we can do because this is a linear network. We turn all of the independent sources to 0, and then we turn them all on, one by one, work out their contribution to the output voltage, and then add up the 3 contributions to the output voltage to give us the final output voltage. So we'll start with the contribution of this 6 milliamp current source here. If we set the other 2 sources to 0, then the circuit we would end up with is this one. A 1K resistor, our 6 milliamp current source. The voltage source set to 0 is replaced by a wire. This current source set to 0 doesn't exist. It's replaced by nothingness. And that gives us this circuit here. Okay, what would the contribution to the output voltage between A and B be in this case? The answer is nothing. Because all of this 6 milliamps is going to flow down through here. This behaves like a current divider. The 6 milliamps is divided between a current flowing through a short circuit, just a wire, and a current flowing through the 2K plus the 2K, or a total of 4K. Well, all of the 6 milliamps is going to flow through the wire, the 0 ohm resistor. So no current is going to flow through these 2 resistors, and with no current flowing through this resistor, there's going to be no voltage across it. So my first contribution to my open circuit output voltage, I'll call it VOC1, is just 0. Next, the contribution of the 5 volt voltage source. If I turn the other sources off, then our current sources again just become nothingness, an open circuit. my resultant circuit then looks like this. This is a 2K resistor, this is a 2K resistor, this is a 5 volt voltage source, that's A and that's B. Once again, this resistor plays no part in the circuit at all. Any current flowing through it has got nowhere to go. We can ignore it. This is a potential divider. It's a particularly easy potential divider to solve because these two resistors have the same value. So the voltage across this resistor will just be half of the voltage placed across the whole potential divider, which in this case would be 2.5 volts. That's my second contribution to my output voltage. Just one to go. The second current source. If I turn the second current source on and set the other two sources to 0, then I would end up with a wire replacing the 5 volt voltage source, a 2K resistor here, a current source of 2 milliamps going down this way, and a 2K resistor here. Well, I've got another current divider. The current flowing into this node here can either flow round this way or it could flow round that way. In both cases, it flows through a 2K resistor to the other side of the current source. So half of the current is going to flow this way and half of the current is going to flow this way. That means that we've got 1 milliamp flowing up through this 2K resistor here, and therefore the voltage between A and B is going to be 2 volts. However, current always flows from the higher potential to the lower potential across a resistor, so B, in this case, would be 2 volts above A. But the open circuit voltage is the voltage at A minus the voltage at B. The voltage at A in this case is below the voltage at B, so the open circuit voltage in this case, the contribution to it, would be minus 2 volts. Apply superposition. My total output voltage is going to be the sum of these three, which is going to be half a volt, 0.5 volts. Does it work? Once again, let's ask the simulator. I've put a diode on the output of the circuit this time, just a normal diode. And yes, with a 500 millivolt voltage source and a 1K resistor in my equivalent network, I'm getting the same output voltage and the same output current. And this would be true no matter what I put across the output terminals of these two networks. Okay, that's the end of examples of Thevenin's theorem for a while. The next talk I'm going to introduce Norton's theorem, which is another way to derive equivalent networks for these two-terminal linear networks.